As wind turbines reach unprecedented heights and blade lengths stretch beyond 100 meters, unexpected challenges are emerging from the field. This week, we welcome back Morten Handberg, the renowned blade whisperer from Wind Power Lab. In this eye-opening discussion, Morten reveals why modern blade designs are showing structural issues earlier than expected and what operators need to watch for to protect their turbines. Stay tuned.
Welcome to Uptime Spotlight, shining light on wind energy's brightest innovators. This is the progress powering tomorrow.
Morten, welcome back to the show.
Thanks, Alan. It's great to be back again.
You are one of our most popular guests. You are the blade whisperer, and anytime I'm at a trade show, people ask, how's Morten doing? How's the blade whisperer doing? Like, well, Morten's great. Morten's super busy, but Morten is great. And they want to have you back on. So here we are. We're back on again. And the topic of today's discussion is about aerodynamic stresses that happen to blades. And we're seeing more problems with that than some of the quality issues. I think it's a combination of quality and aerodynamic issues. What is happening in the field right now with aerodynamic loading on some of these new, longer, more flexible blades?
Well, it's something that's been happening over time. So if we look 10, 15 years back, then the blades were, of course, shorter, and they were a lot stiffer than they were today. They were heavily reinforced, and you could say maybe they were under-optimized, that they had a lot more load capacity than what they needed. And in process of as the blades have become longer, then that buffer have gone away. So because in order to build a longer blade, you had to reduce the thickness of your laminates to avoid an overly bulky structure, but something that could harness the wind in a more efficient way. So that leads to slender, thinner blades that are a lot softer. And we can see that in the natural frequency that the flapwise and edgewise frequencies, they have gone down. And that's because the blades become softer. And that also means that the way that the blade behaves with the wind interaction means that the gravity loads are still a major component, but aeroelastic loading, which adds to shear and torsion loads, have become much more prominent loading conditions on the blades that we see today.
That's interesting. Yeah, obviously, the blades are lighter than they've ever been for the length. I remember being at DTU a year or so ago and looking at one of the first offshore wind blades that Vestas had made, and it was back into DTU's laboratory being examined. And that blade was so stiff and so over-designed that it could have lasted. It could last another 20 years. It had been out in service for 20 years. It could have lasted easily another 20, maybe another 30 years because of the way it was designed, how stiff it was, how short it was. It was like a 20-meter blade. It wasn't that big. But today, when we're talking 60, 80, 100 meters, those blades are just dynamically different. Is it a combination of just trying to lower the cost of the blade, or just the mere fact that the weight is so high or trying to transport it? What's driving down the margins here in terms of the blade design and making them a lot more flexible?
Well, it is an effect by increasing the length, you also increases the power that you can harness from the blade. So it is a desire to create larger turbines, and one of the easiest ways to do that is simply by making the blade longer, because you have to you can do it. It's compared to increasing the swept area or optimizing in other ways. It is a low hanging fruit, and by lowering the weight of the blades, you can also live with a lighter drivetrain, less steel in the tower, smaller foundation. So all of these things play into why that the blade is so much in focus in terms of driving down cost overall, is by reducing the weight of the blades, and that comes as a consequence of it being more. It has less design buffer, and it also will have less lifetime compared to the more conservative blades that we've seen before. And you can say that some of the 2 megawatt turbines, I wouldn't be surprised if you can, from a blade perspective, that you can elongate the lifetime to 30, 40 years because they're so conservatively designed compared to what we see today.
Okay, so adding a kilogram to a blade has consequences all the way down to the foundation, which makes sense when you say it. Okay, so that just adds cost and complexity to every other component in that wind turbine. So the drive then is to lighten the blades and also lengthen the blades at the same time. Th- Now, when we do that, I as I talk to operators around the world, they come back and say to me, "Okay, yeah, that's sure, we're using longer blades. Of course, it creates more power, but they're all being qualified. They're all being tested, right? So we shouldn't have anything to worry about what they're in service." But as the test standards kept up with the rapid design changes that have been made?
Not at all. As I said before, gravity load was the predominant load on all the blades, and that was also what the testing and certification standards focused on. And that's still what's being done today. There are more being done on hybrid loading, combining flapwise and edgewise, but that's still gravity-based loads. We're not taking into account aeroelastic loads when testing and certifying a blade. That's all only done in simulation, and then we learn about what's then happening in operation. So the testing and certification have not kept up with the load conditions that we see on the modern blade.
Okay, so I have a existing OEM that I like using, and I just want to go to the next generation of wind turbines, which is what is happening today. That design of that new wind turbine may not have the same robustness as the one you are used to using, particularly if you've let 5, 10 years go by. So then if you're thinking about the blade design, you're trying to evaluate blade design, you really don't have the data in front of you then. If they haven't tested that for torsional loading, aero loading effects, you really don't know what the history of that blade will be just because you don't have the data, right?
You have no idea what the fatigue lifetime is from these new combined loads, and we are seeing structural blade damages, blade failures happening on wind farms from a variety of wind turbine types, where there is no sign of manufacturing defects. There is no lightning strike. There is no sign of transport damage or failed repair. So it's very difficult to prove exactly what kind of load it is without having the exact model or having other types of data. But when leaving everything out, then you are started to think about, is there some load condition going on here, since we're seeing these buckling related failures in areas where the blade simply shouldn't have any kind of structural damage. And we're seeing a lot on shell sandwich panels, where we see deformation, the damage related to deformation defects. And very early on, actually, the blades are designed for 25 years, but in a wind farm, we can see multiple blades with long transverse cracks over the shell panels, and there's nothing to suggest any kind of manufacturing issue or otherwise that would have allowed for this defect to develop. And that's again one of the things that I think we need to be mindful of with these newer turbines.
So how prevalent is this issue? What should I be looking for in the field?
The need for inspection. We've been saying this for many years, also for the older blades, but it's absolutely equally true. So you need to do at least yearly inspection. Maybe in the early years, do it a bit more often, and do both internal and external, because whatever you see on the outside will likely have started on the inside. So doing an internal inspection is a really important in order to capture the defects in time. Um, and we need to look for, again, what we're looking for is not different from what we did on the traditional blade. They just develop earlier and faster. Looking for structural cracks, looking for debonding, that's typically what you would see. It just develops in the shell laminates. I am less concerned about beam structures in the newer blades than I was before, again, because gravity loads are pretty well understood, and the spark caps and beam structures, they're there to handle those kind of loads. So they're not really as concerned anymore. If you have manufacturing defects, wrinkles in them, that's still a problem, of course. But when we're talking just pure, operation lifetime fatigue, then it's the shell structures that we need to have more in focus, which is opposite, because earlier, the shell was rarely something we even considered as an important part of the structure. So it was rarely in focus because we never really saw any defects there unless there were major lightning strike or otherwise. But they have started to show the defects early on, and that's because that's the weak structure. That's the weak structure from aeroelastic loads.
Okay, that's interesting. So we're seeing more failures early on, probably within the warranty period in a lot of blades, but they're showing up where they normally wouldn't show up. So if I'm an operator, I may not even be looking for this because I wouldn't assume that the shells are the weak point necessarily. I would look for more internal structure issues. What I think is the general method of inspection right now is going to get to the structure. So if you're looking for changes in core or wrinkles on the outside of these blades in places that you would not normally see them, that's your first alarm bell that maybe this is not necessarily a design issue as much as an aero load issue that wasn't evaluated during the qualification phase.
Exactly. I mean, you would do simulations from the OEM, but are they are they accurate enough compared to the wind loads that we're seeing out there? And with the buffer gone, then you might do a simulation for a certain condition of wind loads depending on your wind class. But is that actually then equivalent to the low conditions we see on site? Is ice loading really considered? Um, you know, Ice loading from a gravity sense load, that's not that big of an issue. They can handle that. But when you change the inertia of the blade, then you also change the air light, the share and the torsion load. And again, the shell structures and areas that are susceptible to that kind of loading, they might see then an overloading that you otherwise wouldn't have.
I want to ask maybe a controversial question here because I've been intrigued about this. When I see a lot of these longer, newer blades being installed offshore and they're failing, it seems to happen during the construction phase when they're not in operation. Is that because the turbines maybe not be pointing in the right direction, the yaw is not engaged, and maybe you have 2 of the 3 blades on or something? That the aero loading is then different than what it would be in operation, which is creating unique conditions, that overload the basic design of the blade? Is that the philosophy is what's happening in offshore right now?
I mean, any kind of loading that is where the yaw is off, so the wind is not coming directly towards the blade, is a problematic situation on any account, because the blades are designed for the heaviest load coming, from the front of the blade, leading edge inward. But having loads coming in, from it on the pressure side, suction side shell, or the trailing it, can create load conditions or can create vibration conditions that cause the blade to go into resonance, which can lead to very rapid failures. I guess that there can be yaw situations that don't necessarily lead to a blade failure. That's fine. But again, we're flying blind if we're just allowing the turbine to get wind directions from backwind, side wind, all of that. Then we don't really know uh, when and if that we reach a critical situation. So I would always be concerned. And you could also say, well, the blade was yawed 15 or 50 degrees off from, but the blade didn't break. So obviously the turbine was designed for that. That's not true. You could have just created an overload situation that meant that you shaved off, a few years or 5 years of your lifetime. That doesn't show us an immediate defect, but the blade was still fatigued more than it was supposed to. So you lost a lot of lifetime in that event, but it didn't break. But that's still an issue.
Oh, yeah, it definitely is. So weather forecasting during the construction phase is becoming critical then.
Yeah, yeah. I mean, it's always been an issue, that when the rotary is locked, that you need to get the turbine installed and commissioned as fast as possible so it can start to operate as it's supposed to be. But with lower design margins, the problem have increased in significance, you could say.
That would explain some onshore things that I've seen also. All right, this is fascinating. So we have a problem out in the field. It's really early still. What are some of the approaches to deal with it? Obviously, inspection, probably more frequent inspection, probably during the warranty period because it's going to happen earlier. But what are some of the things that Wind Power Lab and you are recommending right now?
So we're recommending at least yearly inspection, and there are some turbines, wind farms that are receiving um, inspections 2 times every year, some even more often, depending on what kind of conditions that they're seeing. All of that makes a lot of sense because until we have some more data on how these defects develop and what we're seeing, then it is important to have a data because we're dealing with a new generation of turbines where we don't have a lot of historical data to lean on how defects would develop or under what circumstances. So having more frequent inspections is something that we do recommend, and you know, previously we would recommend an in the warranty inspection, and that would be fine. Then you're pretty much good to go. But today, it's you should if you're building a new wind farm today, you should do yearly inspections from day one, in order to avoid critical failures at least.
Let me ask you this question, and uh, I've heard it discussed on certain wind farms, large wind farms, where in windy areas, when the blades are even on the ground. Is there a chance that those blades can get torsional loading that is unnatural or that it wouldn't like to see and could decrease a lifetime?
It's actually an interesting topic. I mean, when the blades are being transported, when they're in storage, they are still introduced to wind to winds, right? So there is still an interaction with the wind that can create its own set of vibrations. It might not be the same resonance that you would see on an erected turbine, but it still is a factor. It's really not well understood how much of an impact it has on the lifetime of the blade, these storage conditions, and something early on it was just not considered. And again, that would have been completely fair because the blades were stiffer, they were more robustly designed. But today it might actually matter. But I think right now we can't really say anything with certainty. But yeah, it is something to look out for. I would definitely say that, but it's not something I can add a lot of details to, unfortunately, because it's something we're still trying to figure out what it actually means for the blade.
Well, would that explain why some of the OEMs and some independent inventors are coming up with these sock designs that go over the blade for a significant portion, probably the outer third of the blade, to disrupt the airflow over the blade so it's not creating lift and maybe not creating torsion in the blade? I've seen a lot more of those recently. Is that the rationale for those?
It is definitely a part of the rationale, something we've seen also during construction that they were applied, and that it's typically something you would do if you know as a constructor that a high wind system is coming in, that is within the limit that can cause edgewise by vibration. Then you can apply one of these socks or nets or however they look, and that will create a disruption of the blade, so it's not allowed to move as freely as it would if it had just been on its own. So that is absolutely something. But yeah, I mean, they are, of course, if you can prevent a blade failure, it's absolutely worth it. But you have to be mindful. It's something that adds to the cost. It's not a trivial thing just to apply a 50-meter sock over a blade. Not at all. And what we've seen in Scandinavia, where we have icing conditions, is that ice can actually then start to build up on the net and start hammering in on the blade, and that can create some structural damages on its own. I would, in general, argue that these damages are lesser than what you would have suffered as if you had seen resonance from edgewise vibrations. The problem is, though, that then instead of having a few cases of really damaged blade, you then see a wide sweep of damages across your entire fleet suddenly, because these nets pick up a lot of things and create some damages to the blade on their own. So it's not a perfect solution, but it's a solution to a problem that we do know is there. So yeah, I I would probably still apply them if I was the owner. But I would also, open my eyes to that. Okay, I'm doing this, but I'm also looking into a repair campaign afterwards anyway. That's just, to be expected, especially if you're in Scandinavia. And I would assume some of the, Canada, some of the Midwestern states, they would have similar conditions.
They do. Does continuous monitoring systems play into this detection at all? Can they pick up some of these aero loading effects, the vibrational effects in them, and detect what they are and give an early warning that maybe you have a problem?
You can absolutely see if something is going on. So I mean, I would generally say any kind of condition monitoring is better than no condition monitoring. Obviously, if we want to learn about the blade behavior that we have, that we have within the wind farm, we want to have sophisticated detection of damages early on, and if we want to get to a point where we can understand what kind of wind conditions actually drive lifetime fatigue, then we need to go for a more sophisticated system that monitors vibration or loads or otherwise. But right now, it's condition monitoring is not a given. And I think for older turbines, it's definitely a good value proposition, but it's really essential for the newer ones because because if you have some kind of damage detection, there's some kind of condition monitoring, you can prevent that you suffer from a complete blade failure. Not a perfect system. There can still happen things, but your risk is lowered significantly. But I would, if you have a larger set of turbines and you want to go into more how do you say, proactive operation maintenance and understand what kind of things are actually driving the damages that I'm seeing. You need to have a really sophisticated either vibration sensor or load sensor that can tell you, well, I got this damage and this was how, but this is how the blade behaved before the event, or during these kind of wind conditions, my vibration signal is tripling or quadrupling, and this is something that is driving my lifetime fatigue.
I want to tap into that lifetime piece, Morton. If blades are not properly aligned in pitch, or they have a lot of leading edge erosion where the airflow over maybe a significant portion of the blade is not normal, not based on what the engineers had on their computer at the time. Does that change aero loading enough where I start to worry as blades age that the aero loading is changing and that I may then induce vibrations or loads later on in life that I maybe wouldn't have seen in year one or two? And do I need to be monitoring for that also?
If you have leading edge erosion, then you are creating more turbulence around your blade. So from a logical perspective, I would say, yeah, that is something that is driving load. I would assume that what the magnitude is, that's difficult to predict again without having any kind of load condition monitoring. Then we have no way of quantifying this. So that again, that's also why it's so important because that it becomes more of a must-have instead of a nice-to-have. These kind of monitoring system. And I would say that both for lightning, but especially for condition monitoring, given what we're seeing in the industry today.
Wow. There's a lot happening in blade design at the minute and then out in the field. It sounds like we have to be more vigilant than ever with these new designs. So, Morton, this is fascinating because I've learned a ton here and I'm trying to absorb it all. So, I'm going to watch this episode on YouTube probably several times after we complete it just to learn all the things you're trying to explain to me because I'm an electrical person. A lot of people you get out in the field also are mechanically inclined. They're not aerodynamically inclined. They're not blade structures people. If they want to get a deeper understanding of what's happening and get some insights from you, how do they do that?
You can reach me at any, well, I would say anytime, not anytime, but you can reach me at Wind Power Lab, and we're always happy to set up a meeting or a call with owners or insurers who want to learn more about the blade problems that they're facing, And in Wind Power, we're all about, knowledge sharing and about raising the bar in the industry so that, we all progressively, learn what it is actually that we have to deal with for the next 25 years. And I think if we can do that, we're also we have a chance that these newer turbines that they are we can increase the lifetime compared to what we would likely look into if we don't, yeah, as you say, become more vigilant in our approach to operation and maintenance.
So you need to reach out to windpowerlab.com. That's their website. A lot of great information on that website, windpowerlab.com. And you can reach out to Morten via LinkedIn. He's available. He's on there. Just reach out to Morten Handberg. Morten, thank you so much for being on the podcast. I really appreciate you coming back. You are our official Blade Whisperer. Love having you on.
Fantastic being here, and thank you so much.